Hello YouTube, it's me Kenny and I'm here with section 1.2. That is row reduction and echelon forms. Really quickly, if you see any way that I can improve, please tell me in the comments. So what I'm going to cover is the echelon / reduced echelon form, more solutions of linear systems, and existence and unique questions once again. Now the definitions that I found that are important are the echelon form and reduced echelon form, what you see in front of you. You may pause at any moment to be able to write it down, or maybe you do what you can with that. There is the leading entry, which is what I'm going to cover first. There's the pivot positions, pivot columns, and pivots. There are basic variables and free variables and general solutions. That would be the definitions that I'm going to cover. There are also two theorems that are very easy that I'm going to cover. I would advise you to pay a little bit closer attention to the second one. The first one as well, yes, but it would be best to pay attention a little bit more to the second one. So I'm going to just start with the definition of a leading entry and what that is, and the echelon forms that are in front of you. First of all, a leading entry is the leftmost non-zero entry in a non-zero row. So let me see if I can show that for you. That would be right towards the middle. So a leading entry would be something like a 1, or you can make it another number, and then that would be your first row, which is leftmost non-zero entry in a non-zero row. This could be one row, and that would fit the criteria of a leading entry. Another something else that could fit the criteria of a leading entry, the definition, would be something like this. And over here, 3 would be the leading entry because it is the leftmost and it is non-zero in a non-zero row. Now that we got that out of the way, we could go back to our echelon form and we could start kind of deciphering what all this means, because it just seems like a lot, and it's probably only because I actually wrote in large print, but that's also for my benefit because I can't see all that well sometimes. Anyway, hopefully it's to your benefit too. So echelon form has 3 properties, and there's an additional 2 properties that if you meet becomes row reduced echelon form. So for now we'll stick to the echelon form. The first property is all non-zero rows are above any rows of all 0. And the criteria here is met with the 5, 1, 2, 0, 3, 1. It is these 2 are non-zero rows, and they're above any all 0 row, which because there is no all 0 row. But if you were to imagine one or write one down, it would still fit the criteria here, as long as it looks more or less like this. Then there is property 2. Each leading entry of a row, remembering what a leading entry is in a column to the right of the leading entry of the row above it. So here I've done that again. Here, how I said my 5 and my 3 are the leading entries. So all entries, no, I'm sorry, each leading entry of a row, is in a column to the right, see it's to the right of 5, of the leading entry of the row above it. This would be the leading entry of the row above it. So this is to the right of 5. If there was a 1 here or some other number here, this would be a leading entry, and that would be to the right of 3, to the right of the leading entry above it here. Then there is the third property. All entries in a column below a leading entry are 0. Let's see, how can I explain this? So over here, I have this here. This is the leading entry. All the entries below the leading entry are 0. Okay? Another leading entry. All the entries below this leading entry are 0. So this meets the criteria for echelon form. Next, what we're going to do is cover 4 and 5 for reduced echelon form. Now, 4 says the leading entry of each non-zero row is 1. So instead of seeing something like this, you would see something like 1, 0, I don't know, 4 something, or 0, I'm sorry, and then something like that. And you would get the identity matrix, which we'll discuss later. So the leading entry in each non-zero row is 1. Okay, here's the leading entry, it's a 1. Here's the leading entry, once again it's a 1. Here's another leading entry, again it's a 1. So number 5, the property number 5 says each leading 1 is the only non-zero entry in its column. Over here, look at the other entries, they're zeros and it's a non-zero entry. Look at the 1, it's non-zero. Look at the others in the column, 0, 0, non-zero entry. Once again, this follows the same pattern. 1 is over here is the non-zero entry. These two are the 0 entry. So this would qualify as a row-reduced echelon form. It's also the identity matrix, how I said. That would be I, if you're curious, I. And it's just this. Or if you were to do a 2x2 matrix, it would just be 1, 0, 0, 1. But I'm getting ahead of myself. Now that I covered that, I could actually remove this here. Put that aside. Okay. Let me see what I've written down here. Okay. Really quickly, I guess I'll cover this. I said this in the last video, but in echelon form, you could see that this is step-like. See? Step-like. Over here, once again, step-like. It doesn't have to be exactly like this, but that will be just general pattern. So now we're going to move on to the section called pivot positions. Here we'll talk about the definition of a pivot position. A pivot position in a matrix A is a 1 as a leading entry of a reduced echelon form of A. So what does that mean? Let's see. Let's see if I could decipher this well for you. So the pivot position, I'll draw another. Of a pivot position in a matrix A, we'll call this A, is a 1 in a leading entry of a reduced echelon form of A, and this is row reduced. Oftentimes we could see it, a pivot position, it doesn't have to be in reduced echelon form, but for the sake of argument, it's easier to see. Here would be the pivot position, this would be the pivot position, this would be the pivot position. Okay, that brings us to the pivot column. A pivot column is a column of A that contains a pivot position. So over here, pivot position, this would be the pivot column. Pivot position, pivot column. Pivot position, pivot column. And finally, a pivot is a non-zero number in a pivot position that is reduced as needed to create zeros via row operation. So let's say you have 4, 1, 2, 3, 0, 5, and then 4, 2, 1. You could choose any of these entries to become the pivot. So you use the such an entry to perform the elementary row operations to reduce these two, any of the other two rows, any of the two columns, any of the two entries in the columns to become 0. So if, let's say I picked 4 of the top row, I would be using 4 to row reduce 3 to 0 and then 4 to 0. Okay, now I'm going to actually perform some of the row operations, row reductions, just a little bit, because we've reached the row reduction algorithm section. By now, I would actually expect you to be more knowledgeable about row operations, and because of 1.1, we're pretty much doing the exact same thing to get something into an echelon form and then eventually to a row reduced echelon form. I know this because I took the class, and some of the homework for 1.1 was I don't know, like 4 questions, 4 very long questions of row reducing to echelon form. But for now, I'm going to use the example in the book. So here we are, bear with me. Zero, 2, -4, 4, 2, -6, 0, 0, 0, 0, 1, 4. Let's see. So now we're going to identify possible pivots. This 3 would be the pivot, 2 would be the pivot, this 1 would be the pivot. That's important for the row reduction, the elementary row operations. So for this, I'm going to draw an arrow. I'm going to divide row 2 by half. And I'm going to get, bear with me, I'm copying this because I did this ahead of time. 4, -3, 2, 5, 0, 2, -4, 4, 2, -6. And it would be very useful if you were to pause the video and try to do these on your own beforehand, even though they're in the book. It's very nice to get that practice in, even though I'm sure if you have the book, you would be doing the homework and getting as much practice as possible. It really helps in the long run because the mental math starts to become very quick. Although it's easy to mess up, so I always do some sort of indication of what I'm doing. Like over here, half of row 2. 0, 0, 0, 0, 1, 4. I'm sorry, not half of row 2, half of row 1. I'm sorry. It's half of row 1. Why would that be half? That should be not half, a third. So you divide 3 by 3, you get 1. 3 by 9, -9 by 3, you get -3. 12 divided by 3, you get 4. 9 divided by 3, you get negative. That's not right. I forgot to copy the 9. And 6 divided by 3, that's 2. 15 divided by 3, that's 5. Then you see row 2, you see that's all divisible by 2, and you say, okay, I could do that. That's very easy. So that is half times row 2. And so you're left with 1, -3, 4, -3, 2, 5, 0, 1, -2, 2, 1, -3, 0, 0, 0, 0, 1, 4. Then I'm going to eventually have to switch to another piece of paper. I don't like that because that kind of ruins where you're coming from. I'm going to have to show both. And that's fine, I guess. We'll do that now then. So this, what I'm going to do is I'm going to take row 1. Remember, you could add whatever you want, whatever row to any other row, or a multiple of a row. So that's row 1 plus 3. That's not right. That should be row 2. 3 times row 2. So the reason I'm doing that, the reason I'm I'm adding row 1 by 3 multiplied by row 2 is because I want to get rid of this negative 3. Okay? That's going to bring us a little bit closer to that will bring us to reduced echelon form. So I want to get rid of this 3. I'm going to write it down here. I'm going to get, that will get rid of our 3. It's not going to do anything to our, I'm writing all the way up here because of habit. So I'm going to write down row 2 first, then row 3. Notice if I multiply this by 3, I get positive 3. If I negative 3 by plus 3, you get 0. Then 2 times 3, that would be 6. 4 plus 6, that is 2. No, that would be negative 2. I'm sorry. Negative 6 plus 4, that is negative 2. Then 3 times 2, that is 6 again. 6 minus 3, that is 3. Then 1 times 3, that is 3 again. 3 plus 2 equals 5. And then 4 times 3 equals 12. 12 plus 5 equals 17. No, that's not right. Why am I not matching? Because I'm multiplying the wrong number. Negative 3 times 2 is 6. Negative 6. Negative 6 plus 5 equals 5. Negative 6 plus 5 equals 1. Right? No. Negative 3 times 2 equals 9. 5, 6, 7, 8, 9. That is a 4. A negative 4. Because that's a negative 9. Okay. Now I'm right. Sorry for all of that. Is stressing the importance of writing things down and keeping everything right mentally. So what I'm going to do, I'm going to speed this up. I'm going to do 2 row operations at the same time. First one is row 1 plus negative 5 times row 3. And the second one was going to be row 2 plus negative 1 times row 3. So row 3 is going to be left alone. The only thing we're going to do is row operations to row 1 and 2. I'm sorry. Yes, 1 and 2. Okay. Just making sure. So we know that 1, 0, negative 2, 3 are going to be the same, because if you do something, if we're using row 3 to do something to row 1 and row 2, then all of these zeros are not going to do anything to any of these entries. Here I use negative 5, that's going to zero this out. Negative 5 plus 5 equals 0. Then 4 times negative 5, that equals negative 20, negative 24. That doesn't seem right. No, negative 20. There should be a 4. This is negative 20. Negative 24. Okay. My notes are wrong. That explains a lot. 2, 2. And now I'm going to use this row operation. 1 times negative 1 equals 0. I mean, plus 1 equals 0. Negative 4 times negative 1 equals, 4 times negative 1 equals negative 4. Negative 4 plus 3 equals negative 7. And then you just write down row 3. And there is our reduced echelon form. Row reduced echelon form. See? Simple, easy, it just takes a while, and it's very easy to mess up the mental math. So now we're going to move into what would be closer to the middle of the lesson. I'm sorry once again, that should not happen. My video quality is poor, and you should love me for it. Okay then. So now we're covering a section called Solutions of Linear Systems. I'm going to pull out one of the examples from the book. 1, 6, 0, 3, 0, 0, 0, 0, 1, negative 4, 0, 5. By the way, the reason I went through the last exercise is so you could see that you go into reduced echelon form and then echelon form and then row reduced echelon form. It goes about talking about an algorithm, but really you're just using row operations to go to echelon form and then go into row reduced echelon form, where you get something that looks very much like the identity matrix that I showed you before. Anyway, so here is the other example. From here we see 3 things that are basic variables, free variables, and general solutions, because it's in row reduced echelon form. Okay, so I'm going to eventually explain what I mean by all of that jargon that you just heard. What I'm going to do is I'm going to convert this into the system of equations, right? Just kind of noticing that it's all in row reduced echelon form. You can see nothing above 0 above the 1, 0 above the 1, all zeros in below the leading entry, 1. Over here, 0 is above this 1. So it's a reduced echelon form, which is nice. It makes things easier. I think I did that for myself just as a little present. Okay, let me finish copying this. 4x4 equals 5, and then x4 equals 7, x sub 4. Okay, so if I try to solve for all these variables, I'm going to get something that looks like let's see, x1 equals negative 6x2 minus 3x4. There's no x2. x3 equals 4x4 plus 5. And then x5 equals 7. All I did is rework things. So x1 is on the left side, everything else was on the right side, like solving for x. I solved here for x sub 3, and I solved here for x sub 5. That's all I did. I could have taken the option of using the first row to solve for x sub 2, but I would much rather sub for x sub 1. Anyway, you can notice that we have the type of potential to solve for x sub 1, x sub 3, and x sub 3. We don't need to solve for x sub 5 because we already know it's 7. The only problem is that we don't have an x sub 4. We have no way of solving for it. And we don't have an x sub 2. We have no way of solving for it. So x sub 1, x sub 3, and x sub 5 are referred to as basic variables because there's a way to get to them. But if you write down what we call the general solution, x sub 1, x sub 2, x sub 3, x sub 4, x sub 5, I'm not sure if you can see that's still on screen, okay. And you start writing things down as so, you get these two guys that are free variables. Free variables as in you could put in anything in them and that would get you the rest of this general solution. Okay, so that covers free basic variables, that covers free variables, these guys. And now that gets me to a general solution, which in this case is this solution here. But it also means that you can use this solution to get every solution. And that's all it means for a general solution. It is implicit. Okay? On matrix linear algebra, I haven't heard the use of the phrase implicit, but it pretty much means every solution possible for this matrix, at least in this context. In case you didn't catch that, that is many solutions, and I'm putting emphasis on that because of our next section, existence and uniqueness questions. Oh, I missed the first theorem. Really quick, I'm gonna just go over the first theorem, even though it's not as important. Let me see if I could find it. I'm having trouble finding it, so I'm just gonna open up my book. But the general gist of it was there is only one. Here it is. The general gist of the first theorem, which I'm not going to write down, is for each matrix, you get one row equivalent matrix that is a reduced echelon form. Okay, so you get one matrix A, you perform the row operations to make it an echelon form. This suggests that there may be many echelon forms that are equivalent to matrix A, Then you row reduce the echelon form matrix into a row reduced echelon form matrix, and that should be the only matrix for that is that is equivalent that is the only row reduced echelon form matrix for matrix A. I'm not going to try to prove that because that's beyond that's the book didn't cover that, which is why I said that it was a lot less important, because you might not need to use that as often as these idea of uniqueness and existence. That's going to bring me to my second theorem. The second theorem is called the existence and uniqueness theorem. It states that a linear system is consistent if and only if you know your math by now, and I'm sure you might, but if and only if means if, I don't know, a pretense, I think that's the word. If something, then something, and if that thing, no wait, how can I write this? If, I'm gonna short it down to IFF because that's what the professors do. If and only if means if a statement, then something, and if something, meaning that same something, is then a statement. All right, that same statement. Okay, I'm not sure if that is clear, but it just means that it has to be true in both directions. So I'm going to use that in this context. If and only if the rightmost column of the augmented matrix is not a pivot column, that is, if and only if an echelon form of the augmented matrix has no row of the form 0 dot 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 0b, with b being a non-zero number. Let me write that down. And that being true in the other direction. So what that's saying is a linear matrix is consistent if you do not have something that looks like 0, 0, 0, dot 0 being equal to b. And if you have this, then it's not consistent. That's all that means. That's all that if and only if means. I'm sorry if I dragged that out a little bit too long. So this means inconsistent. So if you have a row like that in echelon form, then it's inconsistent. If you have no row that looks like this in echelon form or row reduced echelon form, then it's consistent. We saw this in 1.1, where we actually had something like I don't know, 0005 or something like that, which is this 000.0b, and this, when written out as a linear system equation, you get 0 equals 5, which can't possibly be, which is a contradiction, and because it's a contradiction, no solution is found, making it inconsistent. Okay, there is a second part to this theorem. It goes, if a linear system is consistent, so now that we know that the linear system is consistent, then there are two possibilities, there are two solution sets. Either I, a unique solution, when either there is I, a unique solution, when there are no free variables, or I, there's infinitely many variables when there, which we see when there are free variables. So if, let's say, you get something like x sub 1 equals 1, x sub 2 equals 2, x sub 3 equals 3, there is no free variables, And because there are no free variables, there's a unique solution. There's only one. Now, if you get something like I showed you before, x sub 1 equals 1, x sub 2 equals 2, x sub 3 equals x sub 3, making it a free variable, that means there are many solutions. It's a general solution. Because you could choose any x sub 3, I'm sorry, because you could choose any x sub 3, you can place it in this x sub 3, getting x sub 2, any x sub 2 that comes with that x sub 3, and you could put the x sub 3 here, getting that x sub 1 associated with that x sub 3. I hope that wasn't too hard to follow. I believe it was easy, but you guys might tell me otherwise, which is what I'm hoping. And this video has dragged on way too long. This theorem isn't really stating anything new. We already know the definition of a consistent linear system, and we just learned what a free variable is, so I hope that it makes sense. A free variable in a general solution. Let me do some light reading just to be sure that I haven't missed anything. No, it seems that I didn't miss anything. Alright guys, thank you for coming to watch me for a little while, trying to get a better understanding of matrix linear algebra. I would ask you to bear with me because I am going to try doing section by section, and eventually my goal is to do 3 sections per week, maybe Monday, Wednesday, and Friday. If everything goes well, then that might actually happen. I also tied in with work, and also tied in with trying to practice for GREs, and there's the time that I need to actually go through the material again to make sure that everything is correct, and script writing, that I'm going to have a very busy plate. So I would rather my end result looks very well, which is why I keep on asking for comments a lot. I know it's very bad, but I can't improve without feedback. Let me see if I could leave you with what I'm going to cover next week, or not next week, next time. Next time I'm going to be covering vector equations. I'm not sure if that's going to be like a jump in what might be taught in a typical matrix linear algebra course, but it should be easy to get a handle of. You might also see why I start writing this solution as such. That's generally a vector. And, well, I guess I'll leave you here. For now, bye.